Welcome, my name is Filippo Moravido and I am the instructor of the course Riemannian Geometry. The objects of study of this course are Riemannian manifolds, which are smooth manifolds where it's possible to measure angles, distances between points, compute areas and volumes, and introduce several notions of curvatures. This course requires the knowledge of definition of smooth manifolds and the knowledge of the notion of tensors. I know that not all of you have taken the course Differential Geometry MAS 520 for graduate students in mathematics. So I will dedicate some time to review smooth manifolds and tensors. So let's start. In order to present the definition of smooth manifolds, I have to give a definition of topological manifolds. So suppose that M is a topological space then we say that M is a topological manifold of dimension n, or topological n manifold if the following properties are satisfied. 1. M is a Hausdorff space. So this means that for every pair of distinct points P and Q in M, there are disjoint open subset U and V, such that P belongs to U and Q belongs to V. 2. M is a second countable, and this means that there exists a countable basis for the topology of M. And 3. M is locally Euclidean of dimension n, and this means that each point of M has a neighborhood which is homeomorphic to an open set of Rn. More precisely, this means that for each P in M, we can find an open set U containing P an open subset U hat in Rn, and a homeomorphism phi between U and U hat. A coordinate chart or just a chart on M is a pair U phi where U is an open subset of M, and phi is a homeomorphism between U and U hat given by phi of U contain or equal to Rn. If so, so by definition of topological manifold, each point P in M is contained in the domain U of some chart U phi. This follows essentially from the third property we have included in the definition of topological manifold. If phi of P is equal to 0, then we say that the chart is centered at P. Given a chart U phi, U is a coordinate domain for coordinate neighborhood of each of its points. If phi u is an open ball in Rn, then we say that u is a coordinate ball. Similarly, if phi of u is a cube, then u is a coordinate cube. The map phi, this map here, is called local coordinate map, and the component functions x1, x2, xn of phi, defined by the following identity. Phi of p equal x1 of p xn of p are called local coordinates on U. Now we are ready to see a few examples. Let's start with the graphs of continuous functions. So suppose that U is an open subset and f defined on U with values in Rk is a continuous function. Then the graph of f is defined by let's say first is a subset of Rn times Rk, defined by gamma f equal the sets of pairs x, y in Rn times Rk such that x is in U and y is equal to f of x with the subspace topology so let pi 1 denote the projection onto the first factor and let phi be the restriction of pi 1 to gamma f. So precisely I have that phi of x, y is equal to x if x, y belongs to gamma f. We observe that phi is continuous because it's the restriction of a continuous function. It is a homeomorphism because it admits an inverse, and this inverse is continuous. and this is given by phi inverse of x equal to x f of x. This map is clearly continuous because f is continuous. So this says that gamma f is a topological manifold of dimension n, more precisely you have also that gamma f is homeomorphic to u, and the pair gamma f phi is a coordinate chart before I gave you the definition of local coordinate chart. This is a very special case because here I am using the entire topological manifold gamma f. So here I can write instead of local I can write global. And this chart here is called graph coordinates. Second example is given by the spheres. So for each integer n greater or equal to 0, the unit sphere Sn is Hausdorff and second countable because it is a topological subspace of Rn plus 1. It remains to show that it is locally Euclidean. In order to see that, let's denote by ui plus the subset of r n plus 1 with I equal 1 to n plus 1, where the right coordinate is positive. That is ui plus is given by the set of points in Rn plus 1 such that xi is positive, and similarly ui minus is a set where this coordinate is negative. So let's write x1, x2, xn plus 1 in Rn plus 1 such that xi is negative. Let f the continuous function defined on Bn. This is the unit ball in Rn. That defined by this formula. Then for each I equal 1 to n plus 1, it is easy to check that ui plus intersection Sn is a graph of the function xi equal f over x1 xi hat x n plus 1. This symbol means that xi is removed. Similarly, ui minus intersection Sn is a graph of xi equal minus f of x1 xi at xn plus 1. So this says that ui plus minus intersection Sn is locally Euclidean of dimension n, and phi I plus minus ui plus minus intersection Sn with values in the unit ball Bn, given by phi I plus minus x1 xn plus 1 equal to x1 x I omitted xn plus 1 are graph coordinates for Sn. Since each point of Sn is contained in the domain of at least one of these 2n plus 2 charts, then Sn is a topological n-manifold Last example I will present is the one of the product manifolds. So suppose that M1, Mk are topological manifolds of dimension n1, n2, nk. Then the product m1 times m2 times mk is a topological manifold of dimension n1 plus n2 plus nk. Please solve the following exercise. Check that m1 times m2 times mk is Hausdorff and second countable. This is true because M1, M2, and K are topological manifolds, and they are Hausdorff and second countable. Then it remains to prove it's locally Euclidean. So given any point P1, P2, P3, Pk in M1 times M2 times Mk, we can choose a coordinate chart ui phi I for each mi with pi in ui. This coordinate chart exists because mi is a topological manifold. And then we consider the product map phi 1, phi 2, phi k from u1 times u2 times uk with values in r in rn1 plus n2 plus nk. This is homeomorphism onto its image, and this image is a product of open subsets in Rn1 plus N2 plus Nk. So this says that M1 times M2 times Mk is a topological manifold I will write only top man because it's too long, with charts of the form to 1 times U2 phi 1 times phi 2 times phi 3. And now we talk about smooth structures. So suppose that M is a topological N manifold, and if U phi V psi are two charts such that U intersection V is non-empty, then the composite map Psi compose phi inverse defined on phi of U intersection V into Psi U intersection V is the transition map from phi to Psi. Maybe it's a good idea to make a picture. So this is M. Suppose that this is U, this is V. Then we have that phi send U on phi U, and psi sends V onto Psi V. Then the map psi composed phi inverse, send this region marked with the white color onto this region marked with white color. This is phi of u intersection v, and this is psi of u intersection v. So this is a homomorphism I have to erase something, so let's erase this part. We say that two charts u phi and v psi are smoothly compatible if u intersection v is empty or psi composed phi inverse is a diffeomorphism. A diffeomorphism is a map which is differentiable with the differentiable inverse. This sentence makes sense because phi of u intersection v and psi of u intersection v are open subsets of Rn, and differentiability is to be interpreted in the ordinary sense. We define an atlas for M as a collection of charts whose domains cover M. In other terms, if the atlas is given by ui phi I, then we need that the union of ui is cover M. An atlas is smooth if any two charts are smoothly compatible with each other. It's not finished. A smooth atlas is maximal if it is not properly contained in any larger smooth atlas. Now we can define the smooth structure. If M is a topological manifold, a smooth structure on M is a maximal smooth atlas. I want to mention the following proposition. Let M be a topological manifold, then every smooth atlas A for M is contain in a unique maximum smooth atlas, which is called the smooth structure determined by A. And the second part is the one which says that two smooth atlases for M determine same smooth structure if and only if their union is a smooth atlas. And now I want to introduce a bit of terminology. How much time I have? So if M is a smooth manifold, that is a pair MA where M is a smooth manifold. Sorry. Topological manifold. And A is a smooth structure. I want to say again that this is that this is a maximal smooth atlas Then any chart U phi contained in the given maximal smooth atlas is called a smooth chart. From now on, we will suppose that everything is smooth, that is C infinity, and the corresponding coordinate map phi is called smooth coordinate map. There is also the following terminology: smooth coordinate domain or smooth coordinate neighborhood. Now we are ready, I think, for seeing a few examples. One, Euclidean spaces. For each non-negative integer n, the Euclidean space Rn is a smooth manifold of dimension dimension n with the smooth structure determined by the atlas A equal Rn identity of Rn. Of course, this is not a maximal atlas. This is one very simple atlas, which is the one which determines the smooth structure. So I mean, there exists a maximal smooth atlas which contains this one. So I can say that this one determines the smooth structure. This is what we call standard smooth structure on Rn. And the corresponding coordinate map is called standard coordinates. Second example is given by the real line R equipped with the smooth structure determined by the atlas composed also in this case by one chart, R psi, where psi is a map defined by the formula psi of x equal x power 3. Clearly, this is a smooth manifold. Some of you could ask, but this smooth manifold coincide with the one described previously. If we take n equal 1 here, you get an atlas for R. Are they the same manifold? The answer is no, because the corresponding smooth structure is different. So different smooth structure. And the reason of this is the following. The chart R psi is not smoothly compatible with the charts contained in the maximal atlas containing this one. Sorry, the one I erased, this one, with n equal to 1. Why? With the smooth charts of the standard maximal atlas. It's enough to check that it's not compatible with this one, with n equal 1. Let's consider the transition map. In this case, the transition map is given by identity on R composed with psi inverse, and this is given by y power 1/3, and this is a function which is not smooth at the origin. So the smooth structure I am considering on R is not the same as the smooth structure considered before. Example number 3 is the one of the spheres. So we already know that Sn contained in Rn plus 1 is a topological n manifold. Now we have to define a smooth structure on Sn, and in order to do this we let ui plus minus phi I plus minus with I equal to 1, 2, n plus 1 denote the graph coordinate charts we defined before. Let's check that the transition maps are smooth. So suppose that I is smaller than j. What is phi I plus minus composed with phi j plus minus inverse? You can prove that this is equal to u1 ui omitted where this square root here is at jth position. If I is larger than j, there is a similar formula. Instead, if I is equal to j, we have that phi I plus composed phi I minus inverse is equal to phi I inverse composed phi I plus inverse, and this is the identity on the unit ball Pn. So this says that the collection U I plus minus phi I plus minus is a smooth atlas, and consequently it defines a smooth structure on Sn, which is called standard smooth structure. Last example. Smooth product manifolds. So if M1, M2, Mn are smooth manifold of dimension n1 and 2 and k, and let's use k instead of n, sorry. Okay, so I have to stop soon. Then M1 times M2 times Mk with the smooth structure determined by the atlas having charts of the form U1 times U2 times UK phi 1 times phi 2 times phi k is a smooth manifold of dimension n1 plus n2 plus mk. In order to prove that this is true, you use the fact that you already know that this product is a topological manifold, and you have to check that the transition maps are smooth. So suppose that C1 times C2 times CK is a coordinate chart. Then what is the composition of this map with the inverse of phi 1 times phi 2 times phi k? You can check as an exercise that this is equal to C1 times phi 1 inverse, C1 composed with phi 1 inverse times C2 composed with phi 2 inverse and this is smooth because each factor is smooth because by hypothesis psi I composed with phi I inverse is smooth because it's one of transition maps for Mi, and Mi is a smooth manifold. That's all for today. Thank you for your attention.